A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headache.
If you're building anything with AI, check them out. Modal.com. Alright, we are back. And today, we are diving into the world of atoms, solder, and silicon. Daniel sent us a meaty one this time, really getting into the guts of how the world actually gets built. He's asking about the modern hardware manufacturing life cycle. Specifically, how these companies manage their supply chains, the standardization of circuit boards, the absolute chaos that is a bill of materials, and how all that physical assembly stuff actually talks to the boring business software like ERPs and CRMs. Plus, he wants us to look at how AI is currently shaking up the factory floor.
This is a fantastic prompt. I think a lot of people see a finished laptop or a smart home hub and think of it as a singular object, but it's actually the result of 1,000 tiny miracles of coordination. And by the way, before we get too deep into the solder fumes, a quick note that today's episode is powered by Google Gemini 3 Flash. It's the one pulling the strings on our script today.
Gemini 3 Flash, eh? Hopefully, it knows its way around a pick-and-place machine better than I do. So, Daniel's prompt starts with the foundation, the printed circuit board, or PCB. Herman, I know you've spent way too much time looking at board layouts. Why is standardization so critical here? Can't I just draw some lines on a piece of fiberglass and call it a day?
You could, Corn, but your yield would be zero and your house would probably catch fire. The PCB is the literal nervous system of every electronic device, and because of that, it has to follow incredibly strict international standards. The big name here is IPC. If you're in this industry, you live and breathe IPC standards, specifically things like IPC 2021 for design and IPC 6012 for the qualification of rigid boards. These aren't just suggestions. They are the common language that allows a designer in Dublin to send a file to a fabricator in Shenzhen or Texas and have the result actually work.
It's like the building codes for electronics. You can't just put a load-bearing wall made of marshmallows in a skyscraper. Does the standardization extend to the actual materials, or is it just about where the lines go?
Oh, it's everything. It covers the stack-up, which is the literal layering of copper and fiberglass down to the chemical composition of the pre-preg bonding layers. If your fabricator uses a different resin than your designer specified, the board's impedance might shift. In high-speed signals, like the ones in your 5G phone, that shift means the data literally can't get from point A to point B. It just turns into heat and noise. These standards define everything: how thick the copper traces need to be to carry a certain amount of current, how close two wires can be before they arc, and even the performance classes. This is something most people don't realize. Boards are categorized into 3 classes. Class 1 is general electronics. Think of the cheap toy in a cereal box. If it breaks, nobody cares. Class 2 is dedicated service, which covers most computers and phones. They need to be reliable, but they aren't life-critical. And then there's Class 3.
Let me guess. Class 3 is the "my heart needs to keep beating" or "this rocket shouldn't explode" category.
Precisely. It's high reliability stuff. Medical devices, aerospace, military hardware. The manufacturing tolerances for Class 3 are brutal. We're talking about microscopic inspections of every single drill hole to ensure there isn't a single crack in the plating. When you're building at that level, the cost doesn't just double, it 10x's because of the sheer amount of testing required.
But wait, if someone is designing a Class 3 board for a pacemaker, do they use the same software as the guy making the cereal box toy? Or is there a pro version of the design tools?
The tools are similar, think Altium or Cadence, but the rules you plug into them are totally different. In a Class 3 design, the software will literally scream at you if a trace is 0.01 millimeters too close to a mounting hole. It's about building in a margin of safety that accounts for the worst case scenario. If that pacemaker board experiences a tiny bit of vibration or a temperature swing, it cannot fail. Class 1 boards, on the other hand, are designed for cost to fail. You make them as cheap as possible and accept that 2% might be dead on arrival.
So we've got the board, we've got the standards, but a board is just a green piece of plastic without the components. Daniel mentioned the bill of materials, or the BOM. Now, to the uninitiated, this sounds like a shopping list. But I've heard you complain about BOM management before. Why is it such a headache?
Oh, the bomb is the single source of truth, but it's a truth that's constantly trying to lie to you. In a professional setting, you don't just list 10 resistors. You have two different versions, the E-bomb and the M-bomb. The engineering BOM is what the designers create. It lists the parts needed to make the circuit work. But the manufacturing BOM, the MBOM, is what the factory actually uses. It includes the packaging like, do the parts come on a plastic reel or in a tray, the specific tools needed, and even the assembly instructions.
It's the difference between a recipe saying add eggs and the industrial manual saying crack 48 grade. A large eggs using the Model 500 shell smasher and ensure they are at exactly 4 degrees Celsius. But why do they need to be separate? Couldn't the engineer just specify the real size from the start?
They could, but engineers often don't know which factory is going to build the board when they're designing it. One factory might have a machine that loves 8mm tape reels, while another prefers bulk feeders. If the engineer locks in the packaging too early, they might accidentally double the assembly cost. The M-bomb is where the how meets the what. It even includes things like consumables, the solder paste, the glue, the cleaning solvents that don't show up on the circuit diagram but are vital for the factory to actually function.
And if you get one digit wrong in the manufacturer part number, the MPN, you're in a world of hurt.
You have no idea. Imagine ordering 10,000 capacitors, but you accidentally pick the version that's 0.2 millimeters too wide for the pads on your board. You've just bricked a $100,000 production run. That's why a professional BOM in 2026 has to include an approved vendor list, or AVL. You never ever rely on a single source for a part if you can help it. If TI can't ship your voltage regulator, you better have a pin-compatible alternative from analog devices already vetted and in the system.
That sounds like a logistical nightmare, especially lately. I mean, Daniel mentioned this silicon shock of 2026. What's going on there? Is it just the usual supply chain stuff, or is something else at play?
It's the AI gold rush, corn. It's sucking all the oxygen out of the room. We're seeing a structural shortage of high-end materials because the giants like Nvidia and the data center builders are buying up everything. They need specialized PCBs with 20 plus layers and advanced glass fabrics for the H200 and B200 chips. If you're a smaller manufacturer trying to build, say, a high-end medical monitor or a specialized industrial controller, you're getting crowded out. The lead times for the raw materials to even make the circuit boards are stretching into months because the AI infrastructure players have basically pre-booked the entire global capacity.
Is it just the chips, or is it the actual dirt and chemicals too? I heard something about a shortage of specialized copper foil.
It's both. To handle the massive data rates of modern AI chips, you need ultra-low loss laminates. There are only a handful of companies in the world, like Isola or Panasonic, that make the high-end stuff. When Microsoft or Google orders enough for 10 new data centers, they aren't just buying the chips. They are buying the entire production capacity of the laminate factories for the next 6 months. So, if you're a startup building a smart toaster, you're suddenly told that your basic FR4 board material is on backorder because the factory switched all its lines over to the high-margin AI stuff. It's a cascading failure of availability.
So, if you're not building a god box for a data center, you're basically waiting in line behind everyone else. That's a tough spot for innovation. But let's say you actually get your parts. You've got your Class 2 boards and your 5,000 tiny resistors. How does the physical assembly actually happen? I assume it's not just a room full of people with soldering irons anymore.
Not unless you're making boutique guitar pedals. No, the modern SMT surface mount technology line is a marvel of high-speed robotics. It's a closed-loop system. It starts with solder paste printing. You have a stainless steel stencil with tiny holes in it, and a machine squeegees solder paste across it onto the board. But here's the cool part, right after that you have SPI, or solder paste inspection.
Wait, you inspect the glue before you even put the parts on. That seems a bit paranoid, doesn't it?
It's necessary paranoia. Over 70% of defects in electronics manufacturing can be traced back to bad solder printing. Too much paste and you get a short circuit, too little and the part falls off. The SPI machine uses 3D sensors to measure the volume of every single deposit of paste in seconds. If it's off by a hair, the board is kicked out before it ever hits the expensive machines. Think of it like this. If you're building a house and the foundation is crooked, do you keep building the walls? No, you fix the foundation or start over. In SMT, it's much cheaper to wipe a board clean and reprint it than it is to try and fix a bad solder joint after the components are already stuck in it.
That makes sense. Don't waste time building on a bad foundation. Then comes the robot arms, right? The pick and place?
The pick and place or PNP machines are the rock stars of the factory. In 2026, these machines are placing over 100,000 components per hour. That's nearly 30 parts a second. These tiny vacuum nozzles are flying back and forth, picking up components the size of a grain of sand and placing them with micron-level precision. And they're doing it while the machine is vibrating like crazy. It's incredible to watch.
I've seen videos of those. It's a blur. But how does it know it picked up the right part? If the reels get swapped by a tired worker, does the machine just keep happily placing the wrong resistors?
Most modern PNP machines have vision centering. As the nozzle moves from the reel to the board, it flies over a high-speed camera. The camera checks the shape, size, and orientation of the part in midair. If it's the wrong shape, the machine spits it into a reject bin and keeps going. Also, the reels themselves are usually bar-coded. If a worker tries to load a 10k ohm resistor into a slot designated for a 1k ohm resistor, the machine will literally lock its doors and refuse to start until the error is corrected.
I love the idea of a machine going on strike because of a barcode error. But once the parts are sitting in the wet paste, they aren't actually attached yet. One sneeze and the whole board is ruined.
That's where the reflow oven comes in. The board travels through a long tunnel with multiple temperature zones. You have to heat the board up gradually so you don't thermal shock the components. Then you hit the liquidus temperature where the solder melts, usually using SAC 305 lead-free solder, and then you cool it down in a controlled way to form a strong joint. If you do it wrong, you get tombstoning, where a tiny component literally stands up on one end because the surface tension of the solder was uneven.
Tombstoning. That's a great name for a failure mode. It sounds like a tiny electronic cemetery. Is it just a visual thing, or does it actually break the circuit?
Oh, it breaks it completely. One end of the component is waving in the air like it's saying hello, while the other end is stuck in the solder. There's no connection. It happens because one side of the component's pad reaches the melting point a fraction of a second before the other. That liquid solder pulls on the part like a tiny magnet, and if the other side is still solid, the part just flips up. It's a nightmare for the AOI, the automated optical inspection. That's the final step. AI-powered cameras look at the finished board and compare it against a golden board. They catch the tombstones, the missing parts, and the solder bridges. In the old days, you'd have a person with a magnifying glass doing this. Now, the AI does it in milliseconds and feeds the data back to the printers and PNP machines to tweak the process in real time.
So if the AOI sees a bunch of tombstones, it tells the oven to turn the heat up or down.
It's a feedback loop. The AOI says, hey, I'm seeing a trend of poor wetting on the north side of the boards, and the oven controller adjusts the convection fans in zone 4 to compensate. It's a self-healing factory line.
It's wild that it's all automated, but Daniel's prompt takes it a step further. He wants to know how this physical stuff, the solder, the robots, the tombstoning, talks to the business side. He mentioned ERPs and CRMs. I usually think of those as the places where sales guys put their lunch receipts. How do they relate to a pick-and-place machine?
This is where the digital thread comes in, and it's honestly where the most money is made or lost. You have three main systems, PLM, ERP, and CRM. PLM is Product Lifecycle Management. That's where the engineers live. It stores the CAD files, the schematics, and the revision history. When they finish a design, the PLM pushes that BOM we talked about directly into the ERP, the Enterprise Resource Planning System.
And the ERP is the brain of the whole company?
It's the accountant and the warehouse manager rolled into one. The moment that BOM hits the ERP, it triggers something called MRP, Material Requirements Planning. The system automatically looks at what's in the warehouse, what's already on order, and what needs to be bought. If you need 10,000 chips and you only have 2,000, the ERP generates the purchase orders automatically, but it goes deeper. The ERP also tracks work in progress or WIP. Every time a board passes through the AOI machine, the machine pings the ERP. The business side knows exactly how many finished units they have at any given second.
So it's not just a spreadsheet, it's a living map of everything the company owns and needs. But how does the CRM, the sales tool, fit in? Does the salesperson need to know about solder paste?
They don't need to know about the paste, but they definitely need to know about the outputs. Imagine a salesperson in the field lands a huge deal. They enter a lead for 50,000 units into the CRM. The CRM talks to the ERP, and the ERP looks at the factory capacity and the component lead times. It then calculates something called the available to promise or ATP date. It can tell the salesperson, we can deliver these on October 12th because we have a 3-month lead time on the main processor. If those systems are talking, the sales guy promises delivery in 30 days, and the factory manager has a heart attack because the parts won't even arrive for 60.
That sounds like a recipe for a very stressful boardroom meeting. I promised them the moon, and you're telling me we don't even have the cheese for it yet. Is there a fun fact about how these systems talk to each other? Because it sounds like a lot of boring database entries.
Here's a fun one. Some advanced factories now use digital passports for every single board. Every PCB gets a unique laser-etched QR code. As it moves through the line, every machine scans it. By the time it's finished, the ERP has a record of exactly which batch of solder was used on that specific board, which robot placed the chips, and even what the humidity was in the factory that day. If a customer reports a failure 3 years later, the company can scan that code and find out that every board made on a Tuesday in July had a slightly different solder alloy. That's the level of granularity we're talking about.
That is terrifyingly efficient. It's like a background check for a circuit board. And in 2026, we're seeing live BOMs. This is a huge shift. Instead of a static list, the BOM is connected to live market data. If a part goes end of life, meaning the manufacturer is going to stop making it, the system flags it immediately. Or if the price of a capacitor spikes by 500% due to a factory fire in Malaysia, the engineering team gets an automated alert telling them to find a replacement before the next production run. It's no longer a manual process of checking catalogs.
And that's a huge point. In the old days, end of life, EOL notices were sent via email and often got buried. You'd go to start a production run only to find out the main controller hasn't been made in 6 months. Now, the AI in the ERP is constantly scraping distributor websites like DigiKey or Mouser. If the stock level hits 0 across all major vendors, the system triggers a red alert. It might even suggest a replacement part that is currently in stock and has the same footprint.
That sounds like a lot of data to manage. Which leads us to the final part of Daniel's prompt AI. We've mentioned it a bit with optical inspection, but how is AI really changing the way these businesses run? Is it just better cameras, or is it something deeper?
It's getting much deeper than just better eyes. One of the biggest shifts is predictive maintenance. Think about that pick-and-place machine doing 30 parts a second. If a single motor in one of those nozzles starts to wear out, it might still work, but it starts losing a tiny bit of precision. Eventually, it fails, and the whole line stops. That can cost a factory $50,000 an hour in lost productivity.
So, you wait for it to break and then scramble to fix it?
That's the old way. Now, they use Edge AI. They put sensors on the motors to monitor vibration, heat, and even the sound of the machine. The AI can detect the microscopic signature of a bearing that's starting to fail 30 or even 90 days before it actually breaks. The system then schedules the repair during a planned weekend downtime. It turns an emergency into a routine task.
It's like the machine telling you, hey, I'm feeling a little sore in my left arm. Maybe check that out before I have a stroke on Tuesday. Does this AI live in the cloud or on the machine itself?
It's mostly at the edge, meaning the processing happens right there on the factory floor. You can't wait for a round trip to a data center in Virginia when a robot arm is moving at those speeds. The machine needs to make stay-Joe decisions in microseconds, but the clearing happens in the cloud. The data from 1,000 machines around the world is pooled together to train the model, which then gets pushed back down to the individual factory.
Precisely. And then there's the digital twin concept. This has gone from a buzzword to a required tool. Engineers now create physics-based digital twins of the entire assembly process. They simulate the heat flow of the reflow oven on a specific board design. They can see that a certain heavy component might cause the board to warp at 200 degrees Celsius before they ever build a single physical prototype. They're solving manufacturing problems in a simulation, which saves millions in wasted materials.
And it's not just the board, it's the whole factory. They simulate the traffic of the AGVs, the automated guided vehicles that carry parts from the warehouse to the line. If the AI sees that the AGVs are bunching up at a specific corner, it redesigns the factory layout in the simulation. They can run the factory for a simulated year in about 10 minutes to see where the bottlenecks are.
I love that. It's basically measure twice, cut once, but the measuring is done by a supercomputer a billion times a second. But what about the bigger picture? Daniel mentioned silicon sovereignty and geopolitical shifts. How does AI play into that?
This is where it gets heavy. Because of the geopolitical tensions we're seeing, specifically between the US, China, and Taiwan, there's a massive push to de-risk the supply chain. We're seeing companies like TSMC and SK Hynix pouring billions into US-based plants. But you can't just move a factory and expect it to work the same way. The labor costs are different, the regulations are different. AI is being used to bridge that gap. They use AI to optimize the factory flow, basically figuring out the most efficient way to lay out a new plant in Arizona or Ohio to match the output of a legacy plant in Asia.
So AI is basically the equalizer for labor costs. If you can't have 10,000 workers, you have 10,000 smarter robots.
It's called lights out manufacturing. The goal for these new sovereign plants is to be able to run for entire shifts with zero human intervention. The AI manages the inventory, the robots do the assembly, and the predictive maintenance keeps the machines running. It's the only way to make the economics of domestic manufacturing work in a high-wage country. If you can automate 95% of the process, the cost of the remaining 5% of human labor becomes less of a factor.
It's about making the math work when the variables change. If you can't rely on cheap labor, you have to rely on extreme efficiency and automation.
And silicon sovereignty is the goal. Countries want to make sure they can build the chips and the boards they need for their own infrastructure without being at the mercy of a single shipping lane or a single trade dispute. It's a complete reordering of the global economy, and it's all happening right now in 2026. We're seeing a move away from just-in-time manufacturing toward just-in-case. Companies are using AI to predict which components are most likely to be caught in a geopolitical crossfire and are stockpiling those specifically while keeping the rest of the chain lean.
It's wild to think that a tiny resistor on a board is connected to a satellite, which is connected to a sales guy's phone, which is connected to a geopolitical chess game in the Pacific. It's all one giant vibrating system.
It really is. And the companies that survive are the ones that can manage that digital thread from the first line of code in a circuit design to the final delivery at the customer's door. If you lose the thread at any point, if your ERP doesn't know your SMT line is down or your CRM doesn't know your BOM is outdated, you're dead in the water. We're even seeing AI being used in generative design for the boards themselves. You tell the AI the dimensions of the box and the components you need, and it iterates through 10,000 different layouts to find the one with the best thermal performance.
Wait, so the AI is designing the board, the AI is checking the solder, and the AI is predicting when the machine will break. What are the humans doing in this scenario?
The humans are becoming system architects. Instead of worrying about where a single wire goes, they're managing the high-level constraints. They're the ones deciding the performance class and the approved vendor list. They are the pilots, but the AI is the autopilot, the navigator, and the engine flight computer all rolled into one.
Well, I for one am glad I just have to talk into a microphone and not manage 100,000 components an hour. My brain would tombstone in about 5 minutes.
You and me both, Corn. But it's the people doing that work who make our modern world possible. Every time you pick up your phone, you're holding the result of 1,000,000 successful handshakes between these systems.
Truly. All right, let's talk practical takeaways. If you're listening to this and you're in the tech space, or maybe you're an entrepreneur looking at hardware, what should you actually do with this info? For me, the big one is the live bomb concept. Even if you're a small shop, you can't treat your parts list as a static document anymore. You need to be looking at your supply chain as a dynamic moving target. If you don't have an alternative for your critical chips, you don't have a product, you have a gamble.
My takeaway is about design for manufacturing, or DFM. In 2026, there's no excuse for throwing a design over the wall to a factory and hoping they can build it. Use the tools. Platforms like Siemens PCB Flow let you check your design against the actual capabilities of your specific manufacturer before you ever hit send. It saves time, it saves money, and it saves your relationship with your factory manager. Also, don't ignore the middleware. Make sure your PLM and ERP are actually talking. A manual data entry bridge between engineering and production is a 1990s solution to a 2026 problem.
And don't forget the AI angle. Even if you aren't running a massive SMT line, look at where predictive analytics can save you from a stroke on Tuesday. Whether it's your server infrastructure or your physical tools, knowing a failure is coming is worth its weight in gold.
Well said. This has been a deep dive, but a necessary one. Hardware is hard, but it's also where the magic happens. It's the physical manifestation of all our digital dreams, and seeing the complexity behind a single green board really makes you appreciate the engineering talent out there.
Or not absolutely, because I'm not Herman, but I agree. Thanks to Daniel for the killer prompt. It's always fun to look under the hood. Thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes.
And a big thanks to Modal for providing the GPU credits that power the AI systems we use to put this show together. We couldn't do it without that serverless horsepower. It's what allows us to process these massive prompts and keep the conversation flowing.
This has been my Weird Prompts. If you enjoyed this dive into the factory floor, do us a favor and leave a review on whatever app you're using. It genuinely helps other nerdy folks find us. Maybe tell a friend who works in manufacturing. They might find some catharsis in our talk about tombstoning.
You can find us at myweirdprompts.com for the RSS feed and all our social links. We've got the full transcript of today's episode up there as well, including some of those IPC standards we mentioned.
We'll be back next time with whatever weirdness Daniel throws our way. I'm hearing rumors it might be about underwater data centers, so stay tuned for that. See ya.
See ya.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our